All right, ladies and gentlemen, this is, I think, this is the fourth lecture in my physics course for the radiography curriculum at Nashville General Hospital. Um, and I am saddened to say that the text we've switched to barely mentions Newton's laws of motion, if at all. I think they mention maybe something about force, but they don't go into Newton's three rule system, a very simple system to describe. And it's been pared down. I mean, he wrote close to 600 pages, I think, in Principia. Um, and so it's been distilled down to basically three rules. And once you establish these three rules, and then you can start taking measurements of distance and times and things and doing calculations of velocity and acceleration and then tabulating a force, and then you have understanding. Okay, and so Newton's laws of motion are the school book edition of that huge uh, masterwork written when he was 22 years old. Thank God for cholera. That's why he quarantined himself in the first place. And it just gave him a lot of free time in his study, um, where, I mean, you really couldn't, it was a pandemic. You really couldn't go out and about all that much. You had to keep to yourself if you wanted to remain healthy. And so that was the reason he basically locked himself in his study slash observatory and started taking on this project where he would once and for all prove that the motion of the moon, in particular around the Earth, was a result of fundamental rules that the universe behaves by, and all objects behave by these rules. And he was, of course, talking about gravity, and that's what explains the moon's orbit is gravity. But so we'll tiptoe into, now you won't see this supported, like I said, Newton's laws of motion not supported in this current text that we had. Bouchon always seemed to mention it, and I think the other physics author that I've taught out of, Mr. Quinn Carroll, he mentioned it too. But I think it's really fundamental to start with stuff that the students are gonna have real world experience with, and everyone is subconsciously familiar with gravity, even if they don't think about it every day. You live with it every day, and the way that you hold things, the way that you drive your car, the way that you give it more gas when going uphill and give it more brakes when you're going downhill. The way that you know how to fill a cup, everything, every activity that you do and simple task that you perform is done with gravity in mind. Okay, when you're pouring from a pitcher, let's say you have a pitcher filled with orange juice or soda or whatever, and you want to pour it into a glass, you always put the glass below the pitcher, and then you turn the pitcher over so the opening is facing sideways and the liquid pours downwards. And you just take that for granted because that's how it always works. Liquids pour downwards. And so no one would ever put the cup above, like hold the cup above the countertop and start pouring and expecting the liquids to flow upwards. And so gravity is, even if you don't know the rules of gravity and you've never had a lesson in Newton's three laws of motion, you have an intuitive understanding of it. If you've ever learned how to do anything, you had to learn that within a gravitational field. Um, and so that's why I like to include it. And I don't think that we need to get rid of it. I think we need to keep it, even though it doesn't directly relate to anything about X-ray science. If we treat the electron as a particle, then that particle is subject to these three rules of motion. And so that could help us with our understanding about what's happening with the electron when it responds to forces, so like voltage. And so there is that small niche of understanding that is clarified. And I think it's just, I mean, it's nice to jump into a subject matter and have something that you can dream up some examples and make sense of it from your previous experience. And Newton's laws of motion gives us a chance to tiptoe into and introduce the idea that the reality you experience is governed by rules. Okay, and I'm not talking about crimes and legal rules. I'm talking about the way nature behaves. Okay, and the way nature behaves and objects behave and such is subject to rules. And in particular, your understanding of X-ray science is understanding the rules that apply to electrons and their motions, and the rules that apply to photons and their motions, how they propagate, how they interact, so on and so forth. And so a fundamental question of how to get started would be to just take out a piece of paper and write down, to the best of your ability, how do things move? Try to explain it. Okay? Try to, you can use an object. You can say, okay, my ink pen, okay, is resting on the table and it's not moving. And you can say that's because nothing is touching it or messing with it, so to speak. And you can start to develop an idea. Well, how would you make the pen move? Okay. And so then you might say, well, I'd have to pick it up. I would have to grab hold of it, and then move my arm and my hand and my fingers. So there's a grip strength involved, and then there's a flexing of my elbow, right, and maybe a rotating of my shoulder. Okay, and then so what you you might come to the idea that maybe you're imposing a force upon the pen through the grip strength and the other motions, maybe a sum of several forces in several directions, and you end up picking up the pen. Okay? And then you might, like Isaac Newton did, okay, so how does the moon move? Does the moon move? And well, it's pretty apparent to anybody who watches. If you watch in the night sky, you can see the moon move over the course of a couple hours, that it changes position in the sky. So is that moving? Is that the surface of the earth moving, or is that the moon moving past the surface of the earth? And the answer is it's a little bit of both. So, diving deeper, if you're stuck in your laboratory for about 6 to 8 months because there's a cholera epidemic going on in your hometown, and at your university, that you might be tempted to contemplate this and figure out exactly what's happening when the moon moves. Okay. Right, and then this would be a good example. I'm not going to play the video, but you can see that it's a YouTube link. I will be playing it for my live class. But this might, so you might have come up with a definition of motion and force and things of that nature, but then this might have been outside of what you might have been thinking. The gentleman, this is Walter Lewin. He's, I think he's Professor Emeritus. I'm not sure if he's still alive even. He is quite old. These were recorded several years ago. I found his channel. He basically put the entire Physics 1 course for MIT undergrads on YouTube. And it's a fantastic course, and it does give me nostalgia because it's similar to what I encountered at SUNY Brockport as far as the degree of depth covered. But he's got a nice little tricycle with a fire extinguisher rigged to the frame, and then he releases the pressurized air out of the fire extinguisher, and the nozzle is pointing toward the back of the bike. And this is a nice demonstration of Newton's third law of motion, that every action has an equal and opposite reaction. And with the thrust created by the fire extinguisher compressed air cylinder, he's actually able to propel the bike forward at a certain velocity because he's pushing on the air in the room with the compressed air, and the compressed air is pushing back on him. And so therefore he starts moving forward. All he has to do is exceed the coefficient of friction, the friction forces between the tires and the classroom floor, which is with a circular wheel that greatly reduces the entire surface area in contact with the object and allows for forces in certain directions, like down the long axis of the bicycle, to create a rolling motion in the wheels. So yeah, like I said, not going to play that in the midst of the recorded lecture because I'm afraid it would jam it up, and it'd be a little bit too complex for me to upload that to YouTube. So you can look that up on your own on the internet, and I will be playing it live for my physics class. So we're going to talk about distance, we're going to talk about velocity, we are going to talk about acceleration, so there'll be masses involved too. We'll talk about Newton's laws of motion, but I want to make sure that you understand what we mean by velocity, acceleration, and speed, and how is speed different than one or both of those, or are they different at all? Are those all synonyms, or are there differences in between those words? Demonstrate and investigate with examples from common experience. Okay, and so I'll try to, the easiest one is like a falling object, but I'll try to bring up some examples. Distinguish between vectors and scalars. That's a very important consideration, especially when we put cause and effect on those vector measurements. That gives us better understanding of what actually is going on. So it adds more information than just quantification, like we said. Remember Jim and the apples? Well, vectors give us additional information besides the number of the quantity of certain measurements. So demonstrate how weight is a special type of force. I think I touched on that briefly. Weight is basically the measuring the magnitude of gravity on your body. So that's truly what weight means. Mass is the quantity of, so your mass is how much of you there is. Weight is how much force is the earth pulling on you with. Those two ideas are related. If there is more of you, if you have more mass, then your weight will necessarily increase because the force pulling on you increases. So, and then the constancy of acceleration due to gravity. Gravity near the surface of the earth is basically constant. So if you get into low Earth orbit, or if you get to a Lagrange orbit or Lagrange points, or if you get out into interstellar space, gravity is not constant. It's highly variable according to distance, but at extremely finite distances, it turns into a constant value. And so I'll be sharing that information with you for the homework assignments where we do calculations on velocity and acceleration and such. All right, so what is velocity? What is acceleration? Are these things the same, or are they different? Is the gas pedal properly named as the accelerator? Okay, and so spoilers for my live class, velocity and acceleration are not the same. Okay? Velocity and speed are technically, according to a physicist, Also not the same. Um, and those are important distinctions. But that last question, is the gas pedal properly named as the accelerator? Okay. So the gas pedal is kind of weird because it's not a toggle switch. It's more like a lever. Okay. So you push down a little bit and you start going faster. You push down a lot, you start going a lot faster. Okay. And so it's making you change the magnitude of your speed, which is a component of your velocity. And so a change in velocity is acceleration. Okay. The gas pedal is properly named. You step on it a little bit and you accelerate a little bit. You step on it a lot and you accelerate a lot. That is, your velocity changes when you step on it. If you hold it still, your velocity comes to a constant value. Okay. So the act of pressing the pedal more increases velocity. So I would say it is an accelerator, but there's a problem. The brake pedal is also an accelerator. It also changes your velocity over the course of time. You press on the brake pedal, it reduces your velocity over time. And so technically a physicist would say that's, yeah, I mean, if you want to bring in an English major, yes, you would say that's deceleration, or as the physicist might say, negative acceleration, which might break your brain. We'll get to that. Okay. In just a second. All right, so I said no calculus, but this is like baby calculus. Okay, so this is just a Greek symbol. That's delta, that little triangle. So, and it just means change. Okay, and so the way you read this is what's in the parentheses. That's the English equivalent of what the equation is saying. It's saying velocity is the change in distance that an object experiences over the same change in time. And so if you have an object that's moving, it's going to be at position A at a certain time, and then it's going to move to position B at a certain other time. Okay, and so you take the difference of the times, and that gives you the duration of the travel. Okay, and then you measure in meters or centimeters or what have you the distance between position A and position B, and you get to combine that into the idea of a velocity. It also indicates the direction the object is traveling relative to other objects. So you would define, usually for the sake of convenience, the initial direction of travel is always the x-axis, unless you could make it the y-axis or the z-axis or what have you. Or you can define the force vector first as the original direction, and then describe the vector of travel relative to the definition of the force vector. So a lot of people with falling objects, if we're trying to solve a problem with a falling object, we would define the positive x-axis as downward toward the center of the earth. And that way the force that we're dealing with is positive, and the acceleration due to gravity is also a positive number. And then we wouldn't have to deal with pesky negative numbers. Okay? And so it might be that it really is, because relativity is a thing, you can define any original vector, any vector in the problem you're dealing with as moving in, that's what's moving in the positive x direction. So you can be the distance, the direction from A to B could be the positive x direction. It could be up, it could be down, just as long as every other vector you define and every other direction you define, you take into account your original definition of what is motion in the positive x-axis direction, okay? Or the positive y or the positive z. So you can set up your framework however you want, just don't fool yourself later. Make sure that you stick to the diagram that you have started out with. Make sure you keep describing the same thing, okay? And that way your answers will make better sense to you, okay? So calculating a velocity, just as it says, you take the distance traveled, that is, there's a point A and there's a point B, and they're so far apart, okay? And this object is moving from point A to point B, and it takes a certain amount of time for it to move that way. The standard units of measure for velocities in the metric system, in the SI system, is meters per second. That's distance divided by time. Okay, so what is this about vectors and pointing directions and velocities and such? Well, let me tell you a little story. There was once an evil X-ray professor. He didn't have the mustache and the black top hat, but he was evil to the core. And he decides to put a box of newborn puppies on the train tracks. And there is a locomotive on the same rail line, and that locomotive is about, what would we say, 120 meters away, and it's traveling at a speed of 30 meters per second. Okay? Well, this X-ray professor is not as evil as you thought. So how long do we have to rescue the puppies? If the distance between the puppies and the train is 120 meters, and the train is traveling at a speed of 30 meters per second. And you might be tempted to say 4 seconds, but you'd be wrong. And the reason you'd be wrong teaches you the difference between vectors and scalars. Because the puppies are not, in fact, in danger. Well, I told you the magnitude of the train's motion. I did not tell you which direction the train was going. It is heading away from the puppies. And so now, how much time do you have? Well, you have until the next train comes along, I suppose. But you don't have enough information for this. The puppies are not in immediate danger. Okay? What kind of person do you think I am? Come on now. I have a touch of evil, but I use it for good. So now with that example, the reason for that example is to show you the difference between vectors and scalars. Scalars are only magnitude. Things like temperature, time, speed, those are all scalars, like 30 meters per second. Okay? Understand the nuance of 30 meters per second as a piece of information and 30 meters per second away from the puppies. Okay? Those are two different things. You have a different understanding of the situation now that you have the direction included with the magnitude in the second example. And so what I gave you in the first example was the speed of the train. I did say the speed of the train was 30 meters per second, but I didn't say anything about the velocity of the train, because if I had said the velocity of the train, then I would have had to given you the direction too. And that is a vector measurement. A vector measurement has both a magnitude and a direction. Okay? And it follows a cause and effect rule. Okay? And so forces are the causes of accelerations. And so the force vector, the push or the pull, has a certain direction, and the acceleration always has to move in the same direction as the imbalanced force is applied to the object. Okay? You cannot have a force vector applied to an object without the acceleration vector pointed in the same direction as the force vector, because it's the force vector that is causing the acceleration vector. Now, here's the thing. The velocity vector of the object is the sum of the velocity. It is the change in velocity, that is the acceleration, applied to the velocity minute over minute or second over second, plus its starting velocity. So it could be that it was already moving in a certain direction when a force vector was applied to it, and then you would have to do vector sums, which we're not going to do in this physics class. Okay, but acceleration is the change to the velocity. So it has a velocity, let's say 5 meters per second, and then you apply an acceleration or deceleration. Well, that's going to adjust the velocity up or down in the next second that you measure. Okay. And so things that are accelerating are going faster and faster and faster. Things that are decelerating are going slower and slower and slower until they stop. Okay. And then things that we say are motionless, and that's nothing, by the way. Nothing ever stands still. Well, relatively speaking, it's always a comparison. So velocities are always relative. That means when we say something is moving, we mean something is moving relative to me, assuming that I'm not moving at all. Okay. But if you keep looking, if you change your perspective, you'll find that everything is moving. And so the only velocities are relative velocities. That is, typically you have an observer and then you have an object, or you have two objects that you're observing both of them. And either the object is moving past you and you are the second object, or two objects are moving past each other and you're a third object. So either of those, the velocity is relative. That is, the motion is relative to your perspective. Things are either moving or standing still based on whether you're moving or standing still. Okay, and so resting your phone or pen or a book on a desk, and if you sit in a chair, then you would say that those objects that are at rest, have velocities of 0. Okay, but you, the books, the chair, the pen, your phone, any object in the room with you right now, you're all moving on the surface of the entire house that you're in when you're listening to this is on the surface of the earth, and that surface is spinning. Okay, near the equator, it's almost 900 meters. Or is it 900 meters per second? Something like that. It's a velocity. At the poles, it's a little bit slower. At the equator, it's a little bit faster. But you're all spinning around on the globe. Yes, it is a globe. So I'm not going to take the time to prove that here. But I can refer you to some places if you're just insistent. Okay. So these vectors, they have magnitude and direction. And now we do use the real numbers for magnitudes, and so that includes negative numbers. So what does a negative number mean? Well, remember I said the positive x-axis was indication of the initial, it's whatever you define it as. It's either the direction of force or it's the direction of the original motion of the object. If you start out a scenario with an object moving, let's say east to west, 10 meters per second. Well, that's the original direction of motion. If it's slowing down, then the force is actually being applied in the opposite direction. And the way that we represent this with a magnitude is oppositely directed forces and accelerations to the originally defined direction of motion are basically negative. So if you think about the positive x-axis being the positive number line, how would you describe an arrow pointing the opposite way? Well, that's heading toward the negative numbers. And so that's where the convention comes from. So negative magnitudes of acceleration. And this will come up in the homework when we have a truck slowing down. Negative if you calculate the solution, right, and say that it has a positive velocity, but what's the magnitude of the deceleration? If you solve it correctly, you get a negative number for both the acceleration and the force. Okay, if you solve it correctly, and that negative tells you that the arrow vector for the acceleration and the force is in the opposite direction of the original motion of the object. That is, we're pushing on the object in an opposite way to the way that it was originally moving, and that's how brakes work. That's what we mean by slowing down or deceleration. Okay. All right, so now that we have the difference between vectors and scalars sorted, and we have a definition for velocity, now we can talk about inertia, which is basically Newton's first distilled rule. Okay, he says that a body, he calls it a body, but it's an object, what we would call an object. He's talking about matter. He's talking about anything that possesses mass. So it can be anything. It could be a structure with, like a macro structure with billions and billions of atoms and molecules all hanging out together to form an ink pen or a cell phone, or your own physical self, your own body, your arms, legs, and your torso and your head. It could be the moon, right? Because the moon has mass. So basically anything that is matter, and it's got like a boundary to it or a perimeter to it, and it has a certain mass. Solid objects work the best, but volumes of liquids in containers could also be these masses. It will remain at rest or will continue to move with a constant velocity, that is, a specific magnitude and direction, in a straight line along its vector, unless it's acted upon by an external force or an imbalance of forces. So here's the thing, we never really get rid of forces. They're always present. So forces, there's always some, if you have matter present, you have forces present. Because a lot of matter are the sources. The source, oh, that rhymes. That's the sources of the forces is matter. Okay? And there's several different types of forces. There's strong and weak nuclear force. There's ionic and covalent bonds are kind of manifestations of force. There's the Coulomb force, both attraction and repulsion, and that's effectively what an ionic bond is a Coulomb force applied to an atom. And so there's these forces present. There's electrostatic forces, which is also the Coulomb force. You pile up a bunch of individual Coulomb forces and you get a electrostatic force. Okay, and then you also get magnetism, which is kind of it's the same thing as the It's better to call it an electrodynamic force, that it's easier understood. But there's a lot of different forces, and a lot of these forces are dependent upon sources. Charged particles are the sources, like electrostatic attraction or repulsion is the charge itself is the source of that field or that force. Where does the force manifest from? It manifests from the charged particle. It's the behavior of the charged particle. So, um, so when these forces are balanced, then there is no net acceleration is zero, because the forces, one will have a positive x direction, and then the other one, if it's balanced to it, will have a equal magnitude but opposite direction. So it's like you have positive 50 newtons, and then over here, because the arrow is reversed, you'd have negative 50 newtons. You add those together and you get effectively 0 newtons of force. And so that's an object at rest. So when you rest your ink pen or your cell phone or your textbook on your desk, gravity is always pulling on these things toward the center of the earth. But the desk, being a solid object with made of atoms, and all those atoms have outer shell electrons, and so also does your book and your ink pen. Really, they used to call it the normal force, but they figured out it's basically a special condition of the electrostatic force. The reason your pen doesn't fall through the solid desk is because the electrons in the desk are repelling the electrons in the pen. And even though there's no electric current flowing, you still have these orbital electrons around the atom, and repulsion is the default setting. And so solids, the atoms are close enough together that it's a uniform repulsion across the surface. And so you don't really ever touch anything. You get to an electrostatic repulsion before the nucleus in your finger makes contact with the nucleus of an atom in the object that you're touching. And so what we feel as touch is really electrostatic repulsion between the orbital electrons in our fingertips and the orbital electrons in whatever object we're touching. Okay? Now, what does that have to do with inertia? Well, every now and then the forces become unbalanced. Okay? And so you get a object with an unbalanced force. Let's say you hold the pen up in your hand, and then you let it go. You don't set it back on the desk. You let it go in the middle of the air in the room. And what you're going to find is it starts accelerating toward the floor. Okay? Go ahead and run that experiment a couple times until you're satisfied that you get a consistent result. And you can agree that the pen's velocity is increasing right up until the moment that it meets the floor of your room. Okay? You might want to try dropping it from different heights to actually witness the acceleration. It's going to be easier to witness if you hold it above your head and drop it from a greater distance. You will see it starting to go faster and faster and faster as it descends. Okay? Maybe get one of your friends and get out the slow motion camera. And that makes it, if you slow time down by the slow motion camera software in your cell phone, you might see the acceleration more clearly. You might see that it travels further distances in later frames of that slow motion section. Okay? Inertia is the idea that an unbalanced force causes an object to accelerate. So in the case of a falling object, gravity, if there is no normal force, no electrostatic repulsive force given by a solid object, that is, the pen, as soon as I let it go, it's basically interacting with the air, and the air is moving out of the way. It doesn't offer rigid resistance like the desk does. And so we say that the pen is allowed to fall, and it always heads the same direction, down, which is relative to our position on the surface of the earth, but it appears to be heading down relative to us, closer to the floor. Okay? And so do that a couple times and understand what you're demonstrating is inertia. Okay? So while there's a balance of forces on the pen doesn't seem to move. But as soon as you let go of the pen in your hand, now nothing is opposing gravity. There's the air is trying to push back up, but the air is not fixed. The air molecules are not fixed in place, so they literally just roll out of the way and let the pen fall through them. Okay. So inertia, while you're riding a bus or a subway car and the bus is moving at a velocity, your body is also moving at that velocity. But if the bus or the subway car suddenly starts slowing down, you list forward or rock forward every so subtly. And that's because your body's still moving at that constant velocity, even though the bus has stopped. And so you got to brace yourself with that little triangle hand grip to catch yourself from falling forward. And it feels like you're accelerating, but that's a relativistic thing. You're not accelerating. The bus is decelerating relative to you. And so it appears that you're accelerating, that you're moving forward. You're actually maintaining your inertia while the bus is slowing down around you. Okay? Now that is relativistically explained, but both explanations are just fine. If you want to say that the bus is holding still at that moment in time, then yeah, you are accelerating forward. Okay, but it's clearer to think about it. Intuitively makes more sense to say both you and the bus were moving forward, and the bus decided to stop moving forward, but you haven't stopped moving forward yet. And so you were always moving forward, but now it's more obvious because the bus is no longer moving forward. All right, so that's inertia in a nutshell. And so we have to continue now into the next parameter, the next rule. Okay. Imbalanced forces applied to any object cause that object to increase its velocity over time, that is, to accelerate. Okay. And so if you have an object that's still and you apply a force to it, the object will start moving faster. So it'll go from zero velocity to some positive velocity in the direction of motion, so long as the force vectors in the positive x-axis. Okay. If you have an object that is traveling at a constant speed and you push on it to slow it down, then it will lose velocity over time. It will decelerate, and so you'll get a negative number for the acceleration if you solve that. If we're talking about deceleration, that indicates that the acceleration vector is opposite of the velocity vector, and the velocity magnitude is getting smaller and smaller and smaller the longer the event occurs until we get to a velocity of zero. Okay? And so I call F divided by M equals A as the intuitive form. Okay? And that intuitive form is explained by the illustration here. Okay? You have to pull on the wagon to get it to accelerate. Okay? But if the mass increases, then one or two things are going to happen. You're going to apply the same amount of force, but a more massive object won't accelerate as aggressively as a less massive object. That is, the force is proportional to the acceleration, but the mass is inversely proportional to the acceleration as a cause. In other words, heavier things are harder to give a velocity to. You need more force to create the same acceleration in a heavier object. It is easier to make a smaller, less massive object move than it is to make a heavier object move. And this will come up quite a bit. This is the intuitive form and the idea that smaller masses and larger masses, when the same force is applied, you don't get equal accelerations. That's going to come up again when we're talking about the electron. Give me just a second here. Okay. So, yeah, I think that's enough about that. The intuitive form, like I said, for the electron, we're going to find that the electron is one of the smaller masses of any object. It's about the smallest object that still can be called a particle, or having any kind of mass at all. Okay? It's much, much smaller than a proton. And so when we get to electrostatics, electrodynamics, and making X-rays, we're going to find it's much easier to accelerate electrons than it is accelerating protons. Okay, and so what do we mean by acceleration? It is not the same as velocity, it's the change in velocity over time. And so velocity is the change in distance, right? Or the derivative of distance with respect to time. That is, how does distance change when time changes? Okay. Acceleration is how does velocity change as time changes. And so if an object is speeding up or slowing down, that is, the magnitude of the velocity vector is increasing or decreasing, then it's definitely acceleration. But because of vectors and vector summation, which we won't be doing, accelerations applied accelerations applied 180 degrees opposed to velocities, that's called deceleration. Classic acceleration is you apply the force in the same direction the object is moving, and the object moves in that same direction but faster, and so it's just a magnitude increase. What Newton figured out is because these are vectors, accelerations applied across a velocity, that is, not opposed to it, but also not running in the same direction as it, will change the direction and the magnitude of the velocity. Okay, and so this is how objects move around a corner, is the vector part. And so when we apply an acceleration not opposed but not in line with the original motion of the object has to turn to start lining up with the direction of the acceleration. Okay, and that's how we get orbits. Okay. To calculate acceleration, you divide the difference of the starting velocity and the final velocity by the duration of travel, or the duration of the event. Okay. Units of measure are meters per second squared. A negative number is possible and indicates that the object is decelerating. Okay? The direction of the force is the cause applied to the object, which determines the direction of the acceleration. Okay? And so, independent but influenced by acceleration is velocity. So the velocity vector starts out, if the object's moving, and then if we put in an acceleration vector, The direction of the acceleration is determined by the direction of the force, okay, because it's a cause and effect relationship. And then the acceleration vector influences the velocity vector and causes the velocity vector to change, okay? And so eventually the velocity vector will become, if you keep applying the same acceleration vector, the velocity vector will become the acceleration vector. Okay, it'll change direction to align with the direction of the acceleration. Okay. So a car traveling west at 30 meters per second. All right, so west is definitely a direction, so that's a velocity. Okay, it experiences an acceleration of 3 meters per second, and that's in the positive direction, and it doesn't indicate a change in direction. Okay, and so that acceleration vector, because it's positive and it doesn't specifically say any change in direction, the acceleration vector is also pointing west. And so if we draw those vectors, we should draw two arrows, one of them 10 times as large as the other one, because one of them represents 30 and the other one represents 3. Okay, and so you should draw a big arrow for velocity, 30, and then a smaller arrow, 1/10 the size of the original arrow, for acceleration. Okay, but pointing in the same direction. The car is traveling west at 30 meters per second and it experiences a deceleration of 3 meters per second. Now, the magnitudes are the same, so one arrow 10 times bigger than the other, but now the small arrow is pointing in the opposite direction to the big arrow. Okay? If the acceleration and deceleration continue for 5 seconds, what are the final velocities of the car for both scenarios? And for that, you're going to need the acceleration formula and solve for final velocity. Okay. And so on the recorded lecture, I'll give that to you. That's going to be, so your initial velocity is 30. Okay, solving final velocity is what we've got to solve for. Duration of the event is 5 seconds, so we're dividing by 5. So it's 30 minus x divided by 5 equals positive 3 and negative 3. Okay, and so if I applied that, so what I'm going to do is multiply both sides by 5. That will get rid of the 5 in the denominator, and now I'll have 30 minus x equals, in the first case, positive 15, in the second case, negative 15. In the first case, 30 minus x equals 15. X is going to be 15. So the final velocity of the car is 15. 30 minus x equals negative 15. That's gonna be, what do you have to add to 30 to get negative 15? You have to add negative, you have to add, 30 minus 45 in one of the scenarios. And so the final speed of the car in the first scenario should be 45. The final speed of the car in the second scenario should be 15 meters, both of those meters per second. I think I did that math right. Let me pause it and let me scratch something on my notebook real quick. Yeah, so I got that right. I think I quoted the velocity formula wrong, but I did the math correctly in my head. So again, strange brain. Um, but yeah, in the first case, acceleration, you would expect the final velocity to be greater than 30, and it is. It's 45. Okay. And then in the second case, with a deceleration, final velocity should be less than 30, and it also is. It's 15 meters per second. Okay, that's after a duration time of 5 seconds for both scenarios. All right, and so this is the answer to the direction of those velocity vectors. You can see that the velocity, if the car is speeding up, the velocity and the acceleration vectors are pointing in the same direction. If the car is slowing down, the acceleration is applied in an opposite direction to the velocity. In other words, a negative acceleration or deceleration, depending upon if you're a physicist or an English major. Okay? And that gets us to our third law of motion. When one body exerts a force on a second body, okay, the second body simultaneously exerts a force equal in magnitude and opposite in direction to that of the first body. What? Pulls work both ways. Pulling works both ways. So if you pull on a rope, the rope pulls back on you, very much like a tug of war. Okay? If the Earth is pulling you toward its center, you're also pulling the Earth toward your center. Okay? And so forces are, for the most part, forces are applied in equal magnitudes of opposite direction. Okay? Except when it's not, because he says this, then he spent the first two rules talking about an imbalance of forces. So, yeah. But what he's talking about is gravity. Gravity does pull both ways. Okay. But the problem is that intuitive form. We don't see accelerations both ways because we assume that the bigger object, it looks like the bigger object is not moving. Okay. And so just by the simple phrase, jump up in the air right now, we've got a force vector up, and you are the one doing the jumping. You are the one doing the moving. What are you moving relative to? Well, the surface of the earth. That's what we mean by jump up in the air. You are moving your body for a brief moment in time away from the surface of the earth. Okay? And then what happens? Well, then you say gravity kicks in. Well, no, not really. What happens is you're always, even in the beginning of the jump, you're always accelerating toward the center of the earth. It's just for a split second, you extending your legs exerted more repulsive force away from the earth than just for instantaneous moment in time you applied a push against the surface of the earth with your feet, and the earth pushed you back, and so that's why you started accelerating away from the earth. But while Newton's third law of motion kicked in, when you pushed against the earth, it pushed back on you and you jumped. The earth is always pulling on you with gravity through the entire process. And so eventually, the force from your jump goes away, and now there's only one force acting on you, and that's gravity. And so you come back down. Right? And so, does that mean like the space, if you had space shuttle energy generating legs and you jumped with the thrust of the space shuttle, could you launch yourself into orbit? The answer is yes. It's basically the same physics, just bigger magnitudes. Okay, so jumping is kind of like a rocket launch, a very tiny rocket launch that's unsuccessful and you don't achieve orbit. Okay, if you would just ramp up the magnitude of your jump, you could launch yourself into orbit. Okay, so keep hitting the leg press machine. You'll get there someday. Okay. No, actually, your legs would catch fire if you tried to achieve escape velocity by jumping. Your clothes would catch fire from the friction with the air, so don't do that. Yeah. Okay. But equal and opposite also explains why we think it's always the smaller object that's moving, and that's I think I got a nice segue here. Yeah. So we have two objects here, and I'm going to push on both of these things. Okay, which one are you going to observe an acceleration from? Okay, so both of these objects are resting on level ground. A bike that it's a touring bike, so it's made of magnesium frame, so it's ultra light. It only weighs about 10 kilograms. Okay, and I'm going to push on that, right? And then I'm also going to push on a city bus, which weighs about 16,329 kilograms. Which one do you think you'll observe a measurable acceleration with? That's right, the smaller object. So when equal forces are applied to objects large and small, intuitively, we always think of the smaller object as moving. Okay. And so, what about a bicycle versus an aircraft carrier? That's even more ridiculous. If I can't get a bus to move at an acceleration you would quantify at a number greater than zero, I'm definitely not going to cause an aircraft carrier to move if I shove on it with the same force. Okay. And so that example is even more ridiculous. But that's what we're dealing with, this magnitude of almost 10 to the 7th magnitude difference. Okay. What we have in this corner, our first particle is 9.1 times 10 to the minus 31st kilograms. The smallest mass that we know, the electron. Okay. And it is being applied an equal force to this other object that we deal with in X-ray science that has a mass of 3 times 10 to the negative 25th. Still a small object, but an order of magnitude of about 10 to the 9th different with the electron. Ladies and gentlemen, the tungsten nucleus. Okay? And where will we find this tug of war of opposing forces? A force of attraction between this tiny little electron and this massive tungsten nucleus? Well, that's setting the stage for what's happening in the X-ray tube. Which one do you think we're going to be describing as accelerating? That's right. The small object changes its velocity. So it's the electron that accelerates in response to the tungsten nucleus, but we are pulling on the tungsten nucleus with the same voltage that we're pulling on the electron with. It's just the electron is so very small, it achieves a measurable acceleration more easily than the tungsten nucleus does. All right, and so gravity. Gravity is a special force that pulls objects toward large masses. Usually we're talking about planets or stars. Okay, The force of gravity on Earth produces a constant acceleration near its surface. Now, if we get further away from Earth, then gravity starts to thin out a little bit. The force starts to reduce, and so the acceleration starts to reduce. Okay? But when we're talking about the force of gravity while we're sitting here on the surface, then we're going to assume that it's 9.8 meters per second squared. And that number is going to help you with your homework. Okay, so there will be a homework handout that I give out, and it's going to assume that you know the acceleration due to gravity, little g, that's 9.8 meters per second squared. Okay. The direction of gravity is always a downward, perpendicular to a level surface. Okay, and so that helps with the force vector and the acceleration vector. If you're dealing with an object that is falling, the acceleration vector is always applied in a downward direction. Okay. All objects on the surface of the Earth are pulled downward by the center of gravity. The normal force, which I just explained to you, is really the electrostatic force, pushes solid objects in the opposite direction. That's how desks hold up books and cell phones and maybe your lunch and your textbook and your pen and whatever else you set on the desk. It is the atoms within the desk pushing back up on the atoms in the object you placed on it that is repelling gravity. And that's why things don't fall through the desk. If you tried to build a desk out of liquid, then you would find that the liquid moves out of the way and the solid will fall through the liquid just slower. Okay, and then also a desk made out of air. Okay, I wonder if someone could build a desk out of aerogel and you could still rest a solid object on it, because aerogel is weird. It's mostly air, but there is a very thin solid layer, solid to it, solidness, I guess, to it. It's really strange stuff. Okay. So I stand on the floor. Gravity wants to push me through the floor, but the floor is pushing back up on me. So there's a balance of forces. So that's why I don't fall through the floor. Okay. And it really is, it's a combination of the rigidity of solid objects with their molecules so close together and the electrostatic repulsion of each of the atoms involved in those molecules. Those in combination make up what we used to call the normal force. If the normal force is removed, that is, a solid object no longer supports an object placed on top of it, then free fall is allowed to occur. That is, gravity will be the only force acting on the object, and the object will start accelerating in the direction of gravity. So if you get up on top of a very tall building and you hold something over the edge and let go of it, then there's nothing pushing up on it, but gravity is still pushing down on it. It starts accelerating downward. Now, it did say weight was going to be explained. Weight is gravity, but applied to your specific mass. And so weight in pounds is really the magnitude of the force you experience. Okay. And it really is, most of these bathroom scales are spring compression devices. And they know that the spring has got so much potential, like springiness potential in it. They know that it requires a certain force to stretch it and a certain force to compress it. And so they can figure out the magnitude of the force and they can calculate your weight based on the magnitude of the force that you exert, okay, on the spring. Okay, that's usually how a bathroom scale works. But the weight in pounds, they say it's synonymous with your mass. No, it's directly proportional to your mass, but it's not the same as your mass. It's not measuring the same thing. Your mass is always your mass. Your weight is based on the application of Earth's gravity to your mass. And so pounds is your mass factoring in Earth's gravity and the force applied to you. Okay? Your mass is the same even if you're not on Earth. Okay? But your weight changes whether you're on Earth or if you're floating in outer space. All right, that's all I have for Newton's laws of motion. I'm really sorry the textbook doesn't support this. I think it's fundamental to understanding what the electron is doing later, because we are treating the electron as a particle subject to Newton's second law of motion in particular. All right, wrapping up. I'll see you guys later.